time response is consisting of two parts. One is transient response and the other is steady state response. In this unit, we are actually going to study only these two things and related parameters. We have covered already what is steady state response and how we can find the steady state error for some standard test signals. Now, in this lecture and the next few lectures of this unit, we will be discussing different parameters related to the transient response. First, let us consider the time response of a zero-order control system. Zero-order control systems produce an output that instantly matches the input without delay or filtering. Their transfer function is purely a gain. A very simple example of zero-order control system is an amplifier. Let us assume that if there is an input signal which is a linear function, then the output will also be a linear function being multiplied by the constant k. Zero-order control systems are very simple, which do not have any major parameters. Now, let us consider the next case, which is the time response of a first-order control system. A first-order control system is one where the highest power of s in the denominator of its transfer function equals 1. The general form of a first-order control system is k divided by st plus 1, where t is the time constant. Even though this is a general form, but still we are not going to analyze this function. You may think why this is so. To answer that question, you have to focus on the next 4 points which I am going to discuss, because these points are going to help you to solve a huge variety of problems. The first point is, we consider strictly proper transfer functions. Few of you may think that order of a transfer function is defined by the poles of the open loop transfer function, but there is no limitation on the number of zeros in this transfer function. Even though you are technically right, but still, the analysis of improper functions are not present in undergraduate level studies. Even if you take a proper transfer function rather than strictly proper transfer function, then you will get a transfer function in the form like this, which can be simplified in terms of k0 plus k1 divided by st plus 1. If we have taken a transfer function like this, then try to imagine yourself if we have taken a very simple input signal like the impulse input, then the output will also contain an impulse function, which we do not want. An impulse signal in the output represents an output whose value will tend to infinity even for a short duration of time. But for a practical system, we don't want that. For undergraduate level studies, we keep our analysis and understanding of the systems which provide a stable output only. That's why we will consider only a strictly proper transfer function, not even proper transfer function. The second point is, the constant k is removed from the numerator as we have already considered zero-order systems. The transfer function of the general form of first-order control system is k divided by 1 plus st plus 1, which can be written separately like the block diagram which is shown on the screen, where k is written separately and 1 upon st plus 1 is written separately. Here we can say that the block consisting of k is a zero-order system which simply multiplies the input k times to get the output. So eventually, the major parameters or the characteristics of the first order system response will be dependent primarily on the second block which is present in the block diagram. So it will be better if we modify the general form of transfer function by eliminating the constant k. The third point is, we usually consider unity feedback systems, and sometimes formulas derived for unity feedback systems are valid only for unity feedback systems. However, this is not the case here. Here, as you can see, we have considered only the transfer function. The formulas in which the derivation includes particularly the feedback path, such formulas are valid only for unity feedback systems, like the formula of steady state error. But here, as you will see, our analysis will be based on transfer function only. That's why it does not matter whether the system is unity feedback or not. The formula which we are going to study will be valid for both unity and non-unity feedback system. And we have already discussed in steady state error that if there is a non-unity feedback system, then what should you do to convert it into unity feedback systems? But you will think, why we have taken a unity feedback system here? This is only for simplicity. You can take any other closed loop control system, but the resultant transfer function should be of the form 1 upon st plus 1. Otherwise, analysis which we are going to do here will not be valid for those control systems. The fourth point is, sometimes we usually consider negative feedback systems, but you should also know how to convert a positive feedback system into a negative feedback system, which we have already seen in the previous lecture. So, the first 2 points are applicable here. However, the later 2 points are general in nature, which are not applicable in this situation. I just told you all these 4 points so that you can solve a variety of problems even if the block diagram in the question is slightly different from the block diagram through which you have understood the concepts or are very familiar with. Hoping that all the 4 points are clear to you, now I think it should not be a problem to you to understand why we have taken the transfer function of first order control system to be equal to 1 upon st plus 1, and also the block diagram is simply a unity feedback system. Now let us quickly take our first input signal, which is unit step signal, which will give us the Laplace transform of the input to be equal to 1 by s, and as such the Laplace transform of the output will come to be equal to 1 by s multiplied by the transfer function, which is equal to 1 divided by st plus 1. Taking the inverse Laplace transform, we will get the output response to be equal to 1 minus Euler's number raised to the power minus t divided by time constant capital T. The whole expression being multiplied by unit step signal, which simply means that only positive time values are present for the response of the system. As we know already that the time constant of the response is the time taken to reach 63.2% or 1 minus 1 upon e times the final value. Similarly, if we have taken t equal to 2 times of time constant, the output will reach 86.5% of the final value. Similarly, at 3 times the time constant, the response will reach 95%. The same way, when time is equal to 4 times the time constant, the response will reach 98.2% of the final value, and so on. There is no need to learn all the values, but the case when time is equal to 4 times of time constant is special. This is generally referred as settling time. Before 4 times of time constant, the response is referred as the response within the transient period, whereas after 4 times of time constant, the response is referred as steady state response. But 4 times of time constant is a generally acceptable value of settling time. It is not the accurate definition of settling time. The exact definition of settling time is, it is a time required for the output of a dynamic system to reach and remain within 2% error band with respect to the final steady state value. We use the formula of settling time equal to 4 times of time constant when we have to tell the approximate value of the settling time. However, it is slightly less than that value. As you know, to remain within 2% error band, the output should have reached exactly 98%, not 98.2%. That is the reason there is a slight difference between the actual value of settling time to the approximate value which is provided by 4 times of time constant. Also, in the response, you can see that the response is continuously increasing. That's why it is quite easy to find the exact settling time. But sometimes it may not be the case. For example, consider this output. Now tell yourself, what should be the settling time of this response? The answer is 6 seconds. As you can clearly see, even though it reaches 98% of the final value, which is 1, at 2 seconds, but it does not remain within 2% error band. After reaching the value of 0.98 at 2 seconds, the value of the response begins to decrease, which does not satisfy the standard definition of settling time. I hope you have understood this concept. Now let us see the next parameter, which is the rise time. The rise time is defined as the time taken by the output to go from 10% to 90% of the final value. The rough diagram is shown on the screen, where we are actually supposed to find the values of T2 and T1, then only we can calculate the value of rise time. I am going to derive the formula, as it will not only help you in deriving the other formula, but also it is going to help you a lot in solving numerical problems. Our first approach should be to find the final value, which I can clearly say it is 1, but still the formula is simply you have to put the limiting value when t tends to infinity, and you can simply find the final value of the response will be coming out to be equal to 1. Afterwards, you have to put 90% of the final value to find the value of the time t2, and 90% of the final value, which is 1, will come out to be equal to 0.9, and putting the value and solving this equation, you can find the value of t2 to be equal to time constant multiplied by natural logarithm of 10. In the same way, you can find the value of t1, which will come out to be equal to time constant multiplied by natural logarithm of 10 divided by 9. Now, as we know that rest time is equal to t2 minus t1, we will get rest time equal to time constant multiplied by natural logarithm of 9. And if you put approximate value of natural logarithm 9, then you are going to find the approximate formula of rest time to be equal to 2.2 times the time constant. I have also seen questions in competitive exams where you must be using the accurate and exact formulas, because in the objective questions the options are like the difference is very small between the values of the different options, that if you are going to use the approximate formula, you cannot get the exact answer. For that cases, it is very important for you that you know both the formulas. Now let us consider the second case in which the input is unit impulse signal. The Laplace transform of the response in this case will be simply equal to the transfer function, and taking the inverse Laplace transform, the response will come out to be equal to 1 divided by time constant multiplied by Euler's number raised to the power minus time t divided by the time constant, the whole being multiplied by ut, which simply means that the response is present only on the positive values of time. You have just seen that the time constant definition depends upon the final value, but here in this case, you can clearly see the final value is actually 0. Whatever percentage you want to take of 0, it will always come 0. So here, the definition of time constant is slightly different. The time taken to reach 36.8% of the initial value is referred as time constant in this case. And the time constant in these type of cases is also referred as decay time. Now let us see the last case in which the input is unit ramp signal. By following the same method, we can simply find the value of output response, which will come out to be equal to time t minus time constant plus time constant multiplied by Euler's constant raised to the exponential minus t divided by time constant, the whole being multiplied by unit step signal. Here, let us see how we can calculate the steady state error in this case. As you know, steady state error in control systems is usually referred as reference signal or the input signal minus the output signal. By doing that, we can simply find the error signal, and to find the value of steady state error, we have to put the limits when t tends to infinity. By doing so, you will find that the steady state value in this case is equal to the time constant. In this lecture, we have covered the first and zero order systems, and in the next lecture we will cover the second order systems. But before that, let's look at different input signals of first order systems, and let's see if there is a relation between the output of different cases. If you see carefully, then you will realize that if you are going to differentiate the response of unit ramp input, you will get the response of unit step input. And the same way, if you differentiate the output of unit step input, you will get the response of unit impulse input. Before moving to the next lecture, I strongly recommend you to solve a very simple question. and every student usually learns the formulas and his mind simply juggles among the formulas like the formula of settling time, decay time, rise time, etc. They keep thinking which formula to use. But many times tricky questions also come where you should not be using any formula at all, and this question is one among them. 6% error simply means that the response value would have reached 94% of its final steady state value, and that's value we have already applied in the equation. Also, it does not matter whether there is a constant k or not, as you can see clearly that eventually it gets cancelled out. The answer will come 5 natural logarithm of 100 divided by 6 seconds. See you in the next lecture.